Welcome to this introduction to network research. My name is Katharina Bolle-Carbonell and I'm a researcher at Maastricht University. This presentation has 4 parts. The first 3 parts are theoretical, and in the fourth part I will just go into some application of social network analysis. So let's begin with the introduction. Networks are a collection of nodes and edges. Nodes often represent people, but they can also be animals, teams, or organizations. The edges are what links nodes together. This can be advice, trust, friendship. Edges are also called ties, and they are normally assumed to be enduring. This means that if nothing changes, the tie is assumed to keep on existing. A good example is kinship. No matter what you do, your sister will stay your sister. This is in contrast to the view that a tie is a finite action. For example, sending an email or making a phone call. You're not going to make a phone call forever. Those finite actions, they have a clear starting point and a clear end event. Here is an example of how a network looks like. It represents the dependent variable of information sharing. The nodes, so the squares, are all members of the same project and they're all part of the same company. You can see that those nodes have different colors. The different colors represent the area of expertise. Now let's see what else is there in the picture. First, we see squares, as I just said. These are the nodes. In this case, these are people. And as I said, the colors indicate the area of expertise. And if you look closely, you can see that there are many green squares and many blue squares, and that they're sort of clustered together. Secondly, we see lines. These lines are the edges, and in this case represent sharing of information. And lastly, we see arrows, and those arrows indicate who is sending the information and who is receiving it. So for example, at the bottom, we see the square number 15 in orange, who sends information to the square number 12 in green. The figure you just saw was a one-mode network. In a one-mode network, all nodes represent the same thing: all people, all team, or all organization. The figure was also a complete network. A complete network is a network for which you have information about all possible nodes, so in this case, all possible people. This means it is important to define the boundary of your network. In the example, it was being a member of the project. If you don't define the boundary properly, you may have problems collecting the data about enough people in order to conduct the analysis. Because if you don't have enough data, you have missing values, and that is problematic. Based on the project, we can make claims about the network structure of the project teams, but not about the company. For example, it could have been that the project had huge fault lines across their expertise areas, but that does not necessarily mean that these fault lines also exist throughout the organization. Another form of one-mode network is the egonet. In comparison to complete networks, in an egonet, you focus on one specific person, for example, the CEO, and on his or her connection, and on the connection between his or her connections. But you can also collect a two-mode network. This is also called an affiliation or bipart network. In that type of network, your nodes represent 2 different kinds. For example, people and meetings. You will be able to map who attends what meeting. You can imagine that in change processes, such an analysis could be helpful. Somebody who is against the proposed change and attends many meetings with different people has the power to block any change. A two-mode network can be transformed into a one-mode network. About the edges, you can measure them as a binary value, so present or absent, or as value data, as strings of 0, for example, never, to 5 or 10, which means normally very frequently. But keep in mind that not all models and measures take value data, so it is always good to have in mind how you can dichotomize your value data, so what is your cutoff point. Lastly, edges can be directed, then they have arrows, or undirected. Okay, so far we have seen that networks have nodes and edges. If you take them together, you can make different combinations. These are called triadic structures because they have 3 nodes. The different triadic structures make up the network configuration. So the network structure. The network configuration can tell you if the network is centralized, so if it has a number of key players, if there's closure, so a lot of closed triadic structures, giving many ways for information to flow, if there are structural holes, so fault lines in the team, and many other things. You can also use the network structure to estimate what the chances are of a tie existing or not. What is important to keep in mind is that network structures can be decomposed into triadic structures, which themselves can be decomposed into edges. I'll explain why on the next slide. Let's look at a triadic structure with the green nodes. It has the fancy name of a transitive cyclic triad 120C. I give you 15 seconds to see what type of underlying structures you can see in it. An underlying structure is any combination with at least one node and 2 hours. Go! Here, the results. You should have found 4 different combinations. The easiest is the reciprocal relationship, also called a mutual dyad. Then we have those 3 represented at the bottom. We have a 2-pass, an in-2 star, also called popularity, and an out-2 star, also called activity. It is not important to know all these different combinations and their names. It is important to keep this nested structure in mind when explaining why a tie exists between 2 people. Imagine you think that in your network that specific configuration, 120C, is important. It explains a lot about your dependent variable. If you would simply include this configuration, 120C, without its lower order ones, you wouldn't know if the effect of the triadic structure is true or if it is a result of just randomness. What you need to do is include the lower level one. These would control for the structure appearing out of chance. Now, this was the end of part 1. To sum it up, networks are a collection of nodes and edges that give rise to some structure.